All right, so these are the solutions for problems A and B in contest 2. So let's look at problem A first. The statement says that there are 3 cards, each with a positive integer, that we can call A, B, and C. And we need to find the maximal possible sum of the integers written on the picked cards, meaning that we need to find the 2 highest numbered cards, sum them up, and print out the value. So for example, if we have 3, 4, 5, we have to find the 2 highest valued cards, so 4 and 5, sum them up, and print that out. Now, the way to approach this problem is, instead of trying to find the 2 highest numbered cards, what we can do is sum everything up and then remove the minimum valued card out of this list. So for example, if we have 3, 4, 5, we'll sum them up to be 12, and then we're going to remove the minimum value, which is 3, from that, and that's going to give us our answer 9 in this case. Now, the code for this is pretty simple. All we have to do is take the input and then print out the sum minus the minimum value of this list. We're using the min function that comes from this library. If you want to know how to include this, which has a bunch of useful things for competitive programming, you can find the tutorial on the Discord server or ask one of our officers, and we can help. And this is the solution for the first problem. Now, the second problem says we are given 2 integers, a and b, with a less than or equal to b. And we need to determine if the product of the integers following this pattern, I guess, so a times a plus 1 times a plus 2, etc., times b, we need to determine whether that's positive, negative, or 0. So, for example, if we have a equals 1 and b equals 3, what we're going to have is a equals 1 times 2 times 3, and this is going to give us a positive value. Now, there are 3 cases to think of when we're solving this problem. The first case is where both a and b are positive. And this is the simplest because no matter how many positive values you have, if both ends of the range are positive, doesn't matter how many times you multiply them, the results can be positive. So for example, a equals 1 to b equals 99, it's going to be positive. Now, the second case happens when both are negative. And this is the one that's a little trickier because it's going to have 2 different cases. So in the first sub case, let's say, we're going to have an odd number of negative values where, let's say, a equals -3 up until b equals -1. So what this is going to do is -3 times -2 times -1, and this is going to give you a negative result. However, if you have an even number of values, so let's say our range is now -4 to -1, we're going to have an even, -2 times -1. We're going to have an even number of negative values, and that is going to give us a positive result. And now the third case happens when the range essentially crosses 0. So if we have a equals -3 and b equals 2, for example, somewhere down the line, we're going to cross 0, and that's going to zero everything out. So we just print out 0. Now, when thinking about this in code, here is what we can do. So we take the input, and this is going to be our first case, second case, and third case. Now in our first case, relatively simple. If both integers are positive, I'll just print out positive. Now, our second case, it gets a little complicated, but not really. What we're gonna do is we're gonna find the difference between our two negative values, A and B. So remember that A is the first number of the range, B is the final number of the range. Now, what's gonna happen here? Let's say, going back to the example we used, when we have an odd number of numbers, so -3, -2, -1, that's an odd number of negative values, we know that's going to be negative. However, the difference between B and A, so B minus A, is going to be -4, which is even. So let's look at the other case where we have an even number of negative values, and we know that's going to be positive. However, when we do the difference of B and A, we get -5, which is actually odd. So we have to be careful here because it's easy to, I guess, mix things up. However, you need to know that if the difference is even, then it's going to be a negative value. If the difference is odd, then it's going to be a positive value. So that's all that we're doing in our statements here. If the difference between B and A is even, as we saw, we know that's going to have a negative value because it's going to have an odd number of negative values. However, if that difference is odd, we know that it's going to have an even number of negative values, and that's going to give you a positive value. And finally, our else case just goes over the possibility that both of the numbers are not positive or negative, and they're different, so it essentially crosses zero and it zeroes the whole product out. And this was the solution for both problems A and B of the contest.
My name is Aaron. I'm gonna solve the problem C in the contest. The problem statement is that you have to find maximum possible sum of the digits of a positive integer not greater than n. So basically you're trying to find the number which is not greater than n, and the sum of the digits should be maximum. In the sample input 1, this input is 100 and output is 18, because you can find the number 99 which has sum 18, so it is a maximum. The sample input 2 is 99995 and the output is 35, because you can try to find the number with 3 9s and 1 8. As I said before, the maximum sum of the digits will be if you find the maximum length of the number with 9s, so like a bunch of 9s, and it will be the maximum. So for example, for this test case, you can just, here, not 4 digits, right? The maximum sum of the digits with 4 digits is 9999, which is 36, I guess. Yeah. But like this number is greater than this, so you can try just decreasing the length of the number, which is 3 9s, and this will be 27. This answer is possible, but it is not the greatest, so we can try to add, for example, like 1 in the beginning and just 3 9s. This will be 28, but it's still not greatest. But if you type 599, the sum of digits will be 32, and I think that this value is less than the n, and also has a bunch of 9s and 5 at the beginning, which is less than 6 at the beginning. So I think it is the maximum sum of the digits that we can find. Speaking about the implementation, the idea is that we are not trying to save the input in the integer, since it has 10 power 16 numbers, which is a lot. So you just simply can save this number in the array or string, but I'm gonna save it in the array, so I can add, like, find the sum of the digits. I'm saving it in the array in Python. I'm just going through input and save int version of I, and trying to find maximum value of this sum of n. So it is like the original n. I'm just adding all the digits, and the second parameter in the max function is decreasing the first element in the array by 1 and adding 9 multiplied by the length of the array minus 1. And so yeah, that's it. We're gonna try to submit it here. Submit. Copy this. We can do the sample test here, 18. So yeah, it's trying to add 100, it is 1, and decrease the first element by 1, so it's 0, and add 9 multiplied by 2, it is 18. That's why the answer is correct. I'm gonna submit it. Submit. Okay, so yeah, that's it. Thank you.
Hello, I'm Jesse, and today I'll be explaining problem D on our second contest for Competitive Programming Club. So this problem is titled Holidays, and it's from Code Forces. So on the planet Mars, a year lasts exactly n days, and there are no leap years. But Martians have the same weeks as Earthlings, meaning 5 work days and then 2 days off. So we want to determine the minimum possible and the maximum possible number of days off per year on Mars. So that means the minimum and maximum number of weekend days, basically. So in the input, we're just given one number, so positive integer from 1 to 1 million. And then in the output, we want to print the minimum possible and then the maximum possible number of days off. So we can, we're given 2 samples here. So for the first one, we have 14 days, and we have a minimum and maximum possible number are both 4. And then for second input, we're given 2, and then the minimum is 0, the maximum is 2. And then here's some explanations, but I'm going to explain the solution on this whiteboard. So let's say that we're given a number that's a multiple of 7. So let's just start with 7, right? So let's say n is equal to 7. No matter what day of the week we start, we're always going to have 2 days off. So if we started on Monday, let's say, then we would have all these days in the week, right? So this is 7 days, so we'd have Saturday and Sunday. If we started on any other weekday, like, we can see that it's going to include Saturday and Sunday. If we started on Wednesday, it's also going to include Saturday and Sunday. Same thing for the rest of the weekdays. And then if we started on the weekend, it would be the same thing. So if we started on Saturday, we'd have all these days up to Friday. We'd still have Saturday and Sunday. If we started on Sunday, we'd have this Sunday and then the next Saturday. So if we have a multiple of 7, we're always going to have 2 days for that week. And if we had 14, right, so this is the second multiple of 7, then we would just add another week down here, and it would be the same exact pattern, right? So actually we could say like 14 days, if we start on this Monday, then we'd have all these weeks, and then we'd have 4 weekends, right? So it's the same pattern for a multiple of 7. But let's say we are not given a multiple of 7, or let's say we're given something with a multiple of 7 and then additional days. So let's say like 7 plus 3. So let's say n equals 10. So for this 7, there's going to be 2 days off because of the pattern I just talked about. But for the 3, depending on when we start the week, these 3 days are going to change our answer. So if we started these 3 days on Monday, Let me use a different color. If we start on Monday, then we'd have Monday, Tuesday, and Wednesday. There would be 0 days off, right? But if we started on like Saturday or Friday, then we'd have Friday, Saturday, and Sunday. So there would be 2 days off. So we can see that for 3, there's a minimum of 0. Like if we start somewhere here, we'd have 0 days off. And there's a maximum of 2. If we started here, or if we started on Saturday, right, we would also have 2 days off. So the minimum and the maximum are different when we don't have a multiple of 7. Right, so another edge case to notice is that if we have 6, right, if we're given an n of 6, then we're going to have at least 1 day off in the week, because it's going to include Saturday or Sunday somehow. Like if we started on Monday, we'd include the Saturday. Right, if we started on Sunday, we'd go all the way up to, well, not that far. It would be Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, so that's 6 days, and we'd have 1 weekend. So there's no way to place it so that there's no weekends. If we have 6, then we're always going to have at least 1. So for n is equal to 6, or n is equal to a multiple of 7 plus 6, it's going to change the minimum number of days. So we would add 1 to the minimum. But for 5 or less, then we can place it so that, like, if we place it on Monday, then we would have 0 weekends minimum, and then a maximum of 2, right, if we place it somewhere else. So for 5 or less, it's only going to change the maximum. For 6, it's going to change the minimum. And then if it was 7, of course, then it would just be another multiple of 7, and we'd have 2. So let's look at the code. So I have it in Python and C++. I think I'm only going to show the Python one. So first I take the input, and then I divide that input by 7, integer division. So this gives me the multiples of 7, and then I multiply that by 2. So that's the minimum number of holidays. For every week, basically, there's going to be 2 holidays. And then for the extra days, I take the modulus 7. So this is like the 3 here. This is giving me the number of extra days that are not multiples of 7. And then first I'm going to, so for max days, I'm going to set it equal to min, because it's going to be at least the min. And then for the min holidays, remember, if we have 6 extra days, then the min holidays we're going to have at least 1. So we're going to add 1. But if the extra days, or that's for the min holidays. And then for the max holidays, if the extra days is greater than 2, then we can only have a maximum of 2 holidays for a week. If it's less than or equal to 2, then we're just going to add that number of extra days. So if there's 0, 1, or 2 extra days, then we're just going to add that to the maximum. And then those are our answers. We just print that out, and you can see that it works for the test cases. So yeah, I hope you understand the question better, and hope you enjoyed the contest.
Problem E is called erase by value, or in the contest it was called smallest sequence. So you're given a sequence of n integers, and you can either remove all the 2's, all the 4's, or all the 1's. You select one value x, and you can remove all of those copies of that integer from the sequence, and you want to print out this lexicographically smallest sequence. So what does that mean, lexicographically smallest? So let's say you have 2 sequences A and B, A1, A2, A3, B1, B2, B3. Then if A is less than B, that means either A1 is less than B1, or they're equal and A2 is less than B2, or A1 is equal to B1, A2 is equal to B2, and A3 is less than B3. If A1 is less than B1, then regardless of A2, A3, B2, B3, and regardless of, let's say, there is an A4, so it's a longer length, A1 will still be less than B. A will still be a smaller, lexicographically smaller than sequence B. So one thing that you can tell with this problem is that you're always going to be able to create a lexicographically smaller sequence than the original sequence. So you have A is equal to A1, A2, A3, A4 or something, and then you're always able to remove this last element, which if you compare against A1, A2, A3, A4, the original sequence, if all these values are equal and then this sequence is longer, then this original sequence is going to be greater. So you're always able to create a smaller sequence than the original sequence. So that's one thing to look out for. And then the second thing you can notice is that let's say you remove a value and then the second value is smaller than A1. So if A1 and A2 are different values and A2 is smaller than A1, then so let's say you have like 2, 4, 4, 1, 2, and then or let's start with smaller. So let's say you have 4, 2, 2, 1, 4 or something. So the opposite. So let's say A2 is smaller than A1 and you remove the 4. Then the first value is going to be 2 compared to if you choose not to remove 4, then the first value is always going to be 4. So removing the 4 is always going to be better than not removing it because the second value is smaller. So what we can find is that if you get to a strictly smaller number, if you compare I against I plus 1, and this is strictly smaller, then we can stop there and we can just get rid of this I value and set the answer equal to that. And let's say it's increasing, so 1, 2, 3, 4, 5. Then if we remove the 1, then we get 2, 3, 4, 5, and that's going to be a larger sequence. Okay? If you remove 2, if you remove 3, in every case, it's going to be increasing. So this is going to be larger than the original sequence, compared to if we remove the last one, then this is going to be smaller than the original sequence. So if there's a number that's strictly smaller, so 4 to 2, we're going to a strictly smaller number, then we can get rid of this larger value. And otherwise, we want to remove the last value. If it's increasing, so this is sometimes called like monotonically increasing, then you can remove the last value. So the implementation is going to be, so read in the sequence, and then the original default answer is going to be the back, the last C number. And then if this current value is larger than the next value, and remember to be careful about out of bounds check. So this is one way to do it. Then the answer is this value and break. And originally I thought, well, if you check for 4 and let's say it's like 2, 4, 4, 1, 2. If you check for 2 and the next number is larger, then I don't want to check 2 anymore. So I was thinking about adding it to a set or something and just marking that we wouldn't be removing this value in the future. But it turns out that if we go to a larger number and we go down, then we're never removing 2. We're always removing the number that's larger. So it turns out you don't need to use a set or anything like that. And that's how you solve this problem. For the problem cylinder, we're given a horizontal cylinder. And then for each query, we're given either a query of type 1 or type 2. And type 1, we insert in C balls with X written on them, and type 2, we take out C balls from the left. So let's say you have 1, and then you're inserting in X, and then you're inserting in 3 of them. So you'd insert in from the left side, you'd fill it in with 3 X's. And then let's say there's Y and 2 or something, then you're adding in 2 Y's, and then let's say you have 4 or something. Then you take the first 4 elements, and you take, you want to print out the sum of all of these and get rid of them. And so there'd be 1 Y left in the cylinder. So this should be, if you've done data structures before, this is very, very similar to something called a queue. And a queue is basically a line. So if you think about waiting in line, you queue into the back of the line and then you dequeue from the front. And that's also called a push and pop operation sometimes. So you push to the back of a line and then you pop from the front. And then the second thing that you should notice is that these numbers are very large. So 2 times 10 to the 5 is not that large relative to computer speeds, but 10 to the 9, 10 to the 9 are very large. So one issue is if you put in XXX for this operation, this can be 10 to the 9, right? Instead of 3, this can be 10 to the 9. And 10 to the 9 operations, in general, you can only do about 10 to the 8 operations maximum within 1 second. And so that's going to take way more than 10 to the 9 operations. And that's just for one query. You might have to do that 10 to the 5 times. So this is not going to run within time. So we need to kind of condense this information a little bit more. So instead of putting in XXXYY, we can instead do something like if we have this cylinder, this is the queue, then we can put in x comma 3 and we can put in y comma 2. So just like this format with x and c, we can put into the queue, you can put it in a condensed form, and this is going to run within time. And let's say you get 2 comma 4 to 4 as our query, then we want to take the first 4 elements. Then what happens is we take the first number, and then so we're left with 1. If we want to take the first 4 elements, we want the sum first is going to equal 3x, and then the remainder is going to be 1. So we subtract 3, and then we look at the next element and turn this into 1, and then add y to our sum. So I'm using variables here, but you'd have to calculate it out in the actual program. And then the second case is going to be if, let's say you're going to do 2 comma 2 or something. So our query is type 2, and you're trying to get the first 2 numbers and sum them up. So sum is going to be equal to 2 times x, and then we want to change this number to 1. So that's all you have to do, and you can do this literally, and it's going to run within the time limit. So if you look at the code, first, I'm using q, and I'm using a pair of int. So this is just a way of combining the numbers together. And then for every query, you input in the query number, and if the query value is 1, then I create a new pair and insert into the first and second values for the pair and push it into the queue. It's named dequeue, but maybe ignore that. Remainder, then you add in the remainder for query number 2. So let's say it's 2, and the first case is going to be if the front element is greater than the remainder. So if, let's say it's like 3, and this is like 2. So in this case, we want to turn this 3 into a 1, and then add in 2x, right? So this is just literally doing that. So our sum, we're going to start at 0. If we're looking for 0 elements, we want to print out 0. So start at 0, and while the remainder is greater than 0, add in the remainder times the element first. So another thing you can do is actually create like a subclass, and instead of using first and second, it might be more clear to use names like value and count or something like that. So if you want to make it even more clear, you can create a struct or a named tuple or something like that. There's different ways to do it, but that might be an even clearer way to do it. Or you can have 2 queues going, but that might be a little bit more complicated. And then we subtract the count from here. So this front element, I want to subtract 2 from it. So this is just doing that, and then set the remainder to 0. And so this loop is going to end. The second case is going to be when we have something like 4, right? And we want to get rid of this element and go to the second element. And when we get to the second element, the remainder is going to be 1, which is less than this. So we can do this first operation again. So when we have a greater number for this count, what we can do is multiply this first value and the second value and add it to our running sum, and then subtract this second value, the count, from our current value, and we are left with the remainder. And then we can pop off this first element. So we can kind of do this literally. And one thing to watch out for is that you have to cast some of these values to 64-bit integers if you're using a language like C++. So even though this sum value is already 64-bit integer, multiplying two 32-bit integers with each other, this is going to result in overflow, since the max value is like 10 to the 9 and stuff like that. So it's not going to automatically do it for you. You have to state that this multiplication might be greater than a 32-bit integer, and then it'll add it to the 64-bit integer. So you have to literally put this. So if you're too lazy to do that, you can put pair of long, which is kind of longer, but that's another way to do it as well. So that's how you solve this problem.
Okay, so I will assume that you've already read the problem, and we are going to approach this problem by brute force approach, where we look at every possible final number and for each final number we're going to find the minimum time for that specific case. So let's say we are looking at the case where the final number of every slot machine is 0. Then how can we find the minimum time that we can make every slot machine to be 0? And it turned out it's not that complicated as it seems. We can actually just simulate the entire process, and the time complexity is actually fine. So let's see how it actually looks like. When t equals 0, what we can do, we can set any slot machine that has t plus 1 mode 10 as 0. So for instance, when t is 0, t plus 1 is just 1, and mode 10 is just 1. So we are looking at this case. We are looking among these slot machines. We are allowed to set any slot machine that has 0 in this slot. So we are allowed to set S1 as 0 and just finish S1. So let's say we set S1 as S1 in the time step time t equals 0, and t equals 1. T plus mode 10 is t plus 1 mode 10 is just 2. That means we are now looking at this column, and as you can see, since S2 has 0 in this cell, we are allowed to set S2 as 0, which is what we want. So we can just set S2. And for similarly, when time is 2, t plus mode 10 is going to be just 3. And we are now looking at this row. And as you can see here, since S3 has 0 in I equals 3, we are allowed to set S3 to 0. So in total, the time is going to be just 2 for final number 0 case. And actually, if you think about it, this is actually the minimum, because like it's literally the minimum case, right? Because we can set one slot machine to what we want, only one slot machine to what we want in each time step, and we have to set total 3 slot machines, and we kind of finish one slot machine in every step. So like t equals 2 is like really the optimal state. So the problem here is that when we have some duplicate number here, something like this case. So let's say we want every slot machine to be in 1. So we simulate the process as we did before. So when t is equal to 0, t plus 1 mod 10 is just going to be 1. So we can look at I equals 1 row here, and since S2 has 1 in this cell here, we are allowed to set as finish S2 in this time step. So we finish S2, and after that, when t is equal to 1, t plus 1 mod 10 is going to be 2. So we are looking at now this row here, and there is 2 slot machines that has 1 in this place, but we are only allowed to set 1 slot machine in each time step. So we can select S1 or S3, but either case is actually just fine. So let's say we just choose S1. Then after that, we notice that as the time step goes increase 1 by 1, we're essentially stepping to one left like this, right? But like we don't have 1 among this portion, so we have to go this, and this is the important part. When t is equal to 9, t plus 1 mod 10 is 10. So we are now at this row here, and there's nothing we can do right now, but we still have S3 as remaining, so we have to keep going forward. And when t is equal to 10, t plus 1 mod 10 becomes 0. Wait. Oh yeah, this one is supposed to be like this, right? Okay, so t mod 10 plus 1 becomes 1. That means we are now looking at I equals 1. So as you can see, it's kind of unwinds and starts from 1 again. So actually, if you look at T11 case, T mod 10 plus 1 is going to be just 2, because this thing is just 1 and 1 plus 1 is 2. Then now we started from 1, and after one step we go to the 2. So it kind of cycles like this. And after you notice this cycle pattern, you can actually notice that in this time step we have a S3 as a remaining, and this is 1, so we can set S3, and now it's finished. So 11 is going to be the minimum time. And the reason why we are allowed to simulate like this is that because, as you can see, for every cycle we are going to set at least one slot machine. So the actually the maximum time, the worst time possible, is still going to be less than or equal to the 10 times the number of slot machines. Because we finish at least one slot machine in each cycle. What I mean by cycle is like one rewind that happens at like t equals 11. So the solution is going to be quite straightforward. So we just iterate over every final number, and here we just simulate the entire process. So as you can see, if this J refers to the I here, and J refers to the here I here, and here we just start from t equals 0, and if we still have like something, if we still have some slot machines that are not really finished yet, then we just keep going forward. And if you're allowed to, if there's some slot machine that has the number we want as the I equals the current time, then we just like finish that and we remove that from the kind of to-do list. And so finally, after the simulation is done, t is going to be the minimum time, the minimum time that we can set every slot machine to be number 8, and the every possible values are just these values, so we can just take the minimum among them.